Hello guys, welcome to the YouTube channel. I am Krishna Gopal. In today's video, we are going to talk about the Chebyshev inequality. In this video, we are not going to discuss some kind of a question but we are going to discuss this inequality in the deep, because this inequality is very famous and most of the time the interviewer asks you about this inequality in your interview. So it's better to get an understanding of this inequality, why we need this inequality, why we use this inequality, and where we use this inequality. That what we are going to discuss in this video. So let's start the video just by asking why we need this inequality. First question. So to explain you why we need this inequality in the statistics, first thing is that you have to understand the meaning of the standard deviation, which is known as the sigma. So sigma is measured the spread of distribution. Okay, and the spread of distribution is measured by area between the values. Which area we are talking? Which is under PDF between two values of a random variable. Let us suppose we have a distribution whose shape like this, and we have value A here and value B here. So the area under this area is actually controlled between the values of A and B, and this area is actually the probability of X between A and B, okay, of this random variable. So I mean to say here, if sigma is measured by the spread of a distribution, so the sigma is also controlled between two values, that is A and B. Sigma is also controlled by A and B. Let us suppose if you have some distribution, that is a fx 1 upon under root 2 pi e raised to power minus x square by 2, where x lies between infinity and minus infinity. This is the PDF of standard normal distribution. We know this one, whose mean is 0 and standard deviation is 1. So the area between mu minus 1 sigma and mu plus 1 sigma is 68% for this distribution, and mu minus 2 sigma and mu plus 2 sigma is 95% in this distribution. Okay, so this is a straightforward result when we know the distribution. But the thing is that in reality, in most of the time, we don't know what kind of a distribution our data is following. So in that case, can we estimate area between mu minus k sigma and mu plus k sigma for some k, don't know the distribution of capital X. So Chebyshev inequality give the answer of this question by defining. So to define the Chebyshev inequality, we need the random variable. So let X is a random variable. So let X be a random variable whose PDF is fx and mean is mu and sigma is a standard deviation which is greater than 0. So according to the Chebyshev inequality, we have probability of x minus mu less than k sigma is greater than equal to 1 minus 1 upon k square. So this is what the result of Chebyshev inequality. Now to understand this Chebyshev inequality, let's take k is equal to 2. So the k is equal to 2, what the result we have? We have the probability of x minus mu less than 2 sigma, okay, greater than equal to 3 by 4. 1 minus 1 by 4 is 3 by 4. That is a 75% of the values are lies between mu minus 2 sigma and mu plus 2 sigma for the distribution which we don't know. That what our data is following any distribution, but we have no idea about the distribution, but we want to know what number of percentage of our data is lying between two values. For that we need this Chebyshev inequality. Now the most important question comes here, why we need to calculate this area? So the answer is, if you know the distribution, easily we can remove the outlier. But if distribution is not known and we do not want to make any assumption, we do not want to make any kind of a promise to the data, and we do not want to provide any additional information, then how we can detect the outliers in that case? So to detect the outliers in the case when we have no idea about the distribution, we can use the Chebyshev inequality. because it will tell you what number of percentage of your values are lies between this standard deviation. So to check the outliers are present when we have no idea about the distribution, we can use the Chebyshev inequality. Now another thing, where this question is mostly arise. Suppose you are appearing for the research based company. Suppose you are giving an interview for the research based profile as a research engineer in any company. They can ask you, can you prove the Chebyshev inequality? Now why they ask this question to prove your Chebyshev inequality? Because there are the two hidden things are there. First, they can check your statistical knowledge. Second, they can check your calculus knowledge. So both the points are very important for the any research based profile. Okay, so let's see the Chebyshev inequality proof. I'm assuming here let's suppose I have a distribution whose shape is like that, and I don't know what distribution it is, and it have the two bound. This is the, and suppose its mean is here. So I can say mu minus k sigma is here and mu plus k sigma is here, I assume. So to talk about the Chebyshev inequality, one of the most important thing is we talk about the standard deviation, and the square of the standard deviation is the sigma square, that is called the variance. So how we derive the variance? When we know our random variable is a continuous random variable. So let's make another assumption, let x be a continuous random variable. So if x is a continuous random variable, I can use the integration minus infinity to infinity, and it is x minus mu whole square fx dx. Okay, so to solve this integration, I can resolve this integration in three parts, that is minus infinity to the mu minus k sigma x minus mu whole square fx dx plus mu minus k sigma to mu plus k sigma x minus mu whole square fx dx, and the last one is mu plus k sigma to infinity x minus mu whole square fx dx, and this is equal to the sigma square. So this is the first part, this is second part, this is the third part, which I break this integration, which is a capital A, I break capital A in three parts. Now if you see this second part is always positive. When I know this second part is always positive, I can say that sigma square is greater than equal to minus infinity to mu minus k sigma x minus mu whole square fx dx plus mu plus k sigma to infinity x minus mu whole square fx dx. Okay, so now take the case when if x belong to the minus infinity to mu minus k sigma, that is in this case. Okay, if x is lies for this part, if x belong to the minus infinity to mu minus k sigma, that means x is always less than mu minus k sigma. Okay, and this part I can write like x minus mu is less than equal to minus k sigma, and I can write the k sigma is greater than x minus mu. Okay, now I can square it, k square sigma square greater than x minus mu whole square, and I can say this is the second part. You can perform the same analysis for this also. When x belong to the mu plus k sigma to the infinity, so in this case what will happen, the x is always greater than mu plus k sigma, so the x minus mu is greater than k sigma, so x minus mu whole square is greater than k square sigma square. This is your third equation. So from equation 2 and 3, I can write the sigma square in place of x minus mu whole square, it will replace with the k square sigma square. So with the help of equation 2 and 3, I can take a common of k square sigma square, and I can write minus infinity to mu minus k sigma fx dx plus mu plus k sigma to infinity fx dx. So I think up to here is clear. Okay, so we have this equation which we derive here. Okay, now come here, you can directly cancel out each, and 1 upon k square come here, and now Now if you carefully see, this is what? This is the area between two values. That is what? That is the probability of random variable x between two values. So how I can write this one? I can write like probability of x less than is equal to mu minus k sigma plus probability of x is greater than mu plus k sigma. With the help of the modulus property, I can write probability of mod of x minus mu is greater than k sigma, and which we can write, and which is probability of x minus mu, here we change this one to k sigma is greater than equal to 1 minus 1 upon k square. So this is what the Chebyshev inequality we have. So if you are appearing for the research based profile where your calculus, where your statistics knowledge is much more needed, there you can expect this kind of a proof. But this kind of a proof is very easy. Even you see what we did, we just write the sigma square. We should know what is a sigma square, how we write in the case of the continuous random variable. But here I want to clarify one thing. Here we assume it is a continuous random variable. If you want to do this one for the discrete random variable, you have to be replace this integration with the help of a summation. Okay, so what we do, we have to be write how we calculate the sigma square. This is very simple, and then we break this integration into the three parts. And when we break the integration, we say this area is always positive. So we say this is always positive. So this is greater than equal to this first and third part. Now in the first and third part, we have this x minus mu whole square, and x minus mu whole square is common. That means we have to be derive one quantity which can be replaced by both. This is what we study in the definite integration of the 12th class. We derive the second and third equation, and by using the second and third equation, we reach up to here, and up to here we just adjust it by using the modulus property and basic integration property, which give us the Chebyshev inequality. This Chebyshev inequality is very important to know how much your data point is lies between the two values if you don't know the distribution. So I hope this video is clear and the Chebyshev inequality is clear. If you have any doubt regarding the Chebyshev inequality, please let me know in the comment section so I can help you in a better way. And if you like this video, then please like and share and subscribe to my YouTube channel for the more videos. Up to that, thank you and take care and bye bye.